Hi everyone, this is Gene Nech with Eurekademics, and today I'm going to be covering exponential functions to get you ready for your exam. Alright, so the two types of functions that you're going to be dealing with are exponential functions, which are going to be in this format, the blue line. So you're going to have like an a constant number, and it's going to be positive or negative. That's the first thing we check for. And then it's going to be a fraction, less than 1, or 1 or greater than 1, right? So like greater than 1 or less than 1. And then that changes kind of the curve, and we'll explore how that works. And then the inverse functions of exponential functions, by the way, so if you like invert this function, you get a log function. So the inverse of the exponent is the log, and then you're going to graph both. So log functions look like this. They start at 0, and they kind of taper off to 0, okay? So number 11 from your practice problems, we have f of x is 3 to the power of x. So our exponent, our variables in the exponent, so you're dealing with an exponential function. Step 1 is to check the a value. Is it less than 1 or greater than 1? It's greater than 1, so we're dealing with this case. If it was less than 1, it would go down. Excuse me, if it was negative, it would go down. So if step 2 would be to set x to 0. Okay, so if I put 0 into here, anything to the power of 0, you get 1. So that's kind of your first point. Okay, so if x is 0, well then the equation is going to, or function is going to produce 1, right? So then you get your y-intercept of 0, 1. There it is. Your domain is negative infinity going to infinity. Your range starts at 0 going to infinity. It's increasing always and decreasing never. Number 13, we have f of x is 2/3 to the power of x. So first thing we check is our a value. Because our a value is less than 1, it's a fraction, the equation changes a little bit. It starts at infinity and tapers off to 0, okay? So when it was greater than 1, or like normal, it starts 0 and kind of goes up to infinity exponentially. That's like the standard form, right? Normal form, I mean. And then when it's a fraction or less than 1, it just flips. It starts from infinity going tapering down. And then you just plug in some points. So like you would like try 1 and then see what you get, right? You get 2/3. And then that's it. Like 1, 2, 3, and you're good. Try 2 and then see what you get. And then so here we go. We got our y-intercept. The domain is negative infinity to infinity. Our range is 0 to infinity. And it's increasing never, decreasing always. Negative infinity to infinity. All right, so same thing here. We have two equations. We're going to compare them. So on this one, I only graphed the second equation, g of x, because the standard one for of x, we just kind of dealt with. It just would go through the 1, right? So our standard equation goes through the 1, because if you plug in 0, anything to the power of 0 is 1, right? So our f of x was going through here. That plus 2, you take 1 and you have to add 2 to it. So plus 1 plus 2. That plus 2 acts as a vertical shift on the y-intercept. Okay, so let me say that again. That plus 2 acts as a vertical shift on the y-intercept. Number 17, so this time I graphed both of them for you. So your original equation is 3 to the power of x, which is your standard exponential function going through 1. And then we modified the second one, g of x in blue, we have 2/3 to the power of x minus 5. And the minus 5 is on the outside. It's not part of the exponent, so it acts as a vertical shift, okay? So again, we're going to vertically shift from the 1, because that's our y-intercept from here, down 5 points. 1, 2, 3, 4. 1, 4, that's right. So this is 5, 4, 3. 4. Interesting. Oh yeah, that's right. It lands at 4 because 1 minus 5. That's right. So 1, 2, 3, 4. There we go. 4. Sorry. And a is positive, so the whole thing's going up. If a was negative, we would just flip it. It would be going like down, like that. So here we go. So far, so good. All right, number 19 introduces like the application of like these exponential functions. So like these exponential functions like you were just studying, that's how interest works. So like, for example, if you were to put away $500 right now, and it's going to grow at an interest rate of, I don't know, like 5%, and you were to put it away for like let's say 5 years, the time you go off to college, you can actually figure out how much interest you're going to make. Or then you can use this one. These are the 3 different types of formulas. The simple interest formula is IPERT, and then these 2. For number 19, you're using this equation because you have compounding interest, which I'm going to explain. That happens, so this n tells you that's where it happens. That's the number of times that interest happens per year, right? So with this one, you just get credited your 3%, 5% interest rate at the end of the year. So that happens every year, once a year. These are the cases that we're going to explore when n is different. So I'm going to run through this. I don't have the numbers here, but I'll just tell you. So I'm going to use this. So principal, we put in 250. Okay, so I plugged in the formula and the value. So you're putting in your 500 into the P, 1 plus, your rate is in decimal format, 0.07 divided by 1 for this case. Raised to the power of 6 is this number. So now for the 4 calculation, you're going to do the same thing, okay? So where is that thing? We're going to do 1 plus the rate, or the interest of this number, the 4, that's n. So let's take our rate right here, r, and divide that by n first, because like I'm going to calculate it, right? So 0.07 is the rate. That's where I'm going to start with. Now I'm going to divide that by this 4. Equals this. We're going to add the 1, so we're going to take care of this little 1 hanging out, plus 1. We're going to raise it to the power of 6 because that's the amount of years we're doing it for. So to the power of 6 equals this. And then we're going to multiply it by our investment times $500. Boom. And 933, right? And then I'll let you do the rest. You're just changing that n down here to 12,365. And then for continuously, use this equation. So you're just going to do P, or 500 times, E is 2.71, times to the power of 6 times the rate. Yeah, 0.07 times 6. So to the power of 0.07 times 6, and that'll get you there. Okay. There's only one of these, so just make sure you have these 3 equations, and then you just assign the right variables, and you're dealing with it. All right, so these are the log problems. So the way that you translate it is it's this base to the power of x equals this number. So it's like 2 to the x is 32, so that's 5, because 2 times 2 times 2 times 2 times 2 is 32. Same thing here, we do 25 to the power of x is 5. Well, if x is like a square root, or like you square root it, right? If you use half as the exponent, that means square rooting, and you get the 5. Okay, so natural log e to the power of 11. Anytime you have an exponent to the power of something, so here it is, rule number 3. That exponent jumps in front and multiplies out. So we have 11 times natural log e. One of the rules of natural log is natural log to its base e is just 1. So you have 11 times 1, which is 11. Anytime it doesn't specify the base is 10. So we have 10 to the power of x equals 80. Well, that's 8, because 10 times itself 8 times is 80. No, wait, I messed up. That's not 8. That's not 8. So x would be 80 to the 1/10, right? To the 10th root. That's better. There we go. All right, so now we're going to graph 2 logs. So we have a natural log, which is in green. Natural log goes through 1, okay? So our exponential functions, we're going through the 1 on the y-axis. Our logs kind of typically center on this number on the x-axis. And then when it's negative, it gets like flipped, all right? So instead of starting from here, it starts in this quadrant and coming down. And then the +4 acts as a horizontal shift left 4. 1, 2, 3, 4. Okay? Because horizontal shifts are opposite direction. Remember that. Number 31, you have natural log x, which is here. Oh, I messed up my colors. This one should be blue. All right. Bear with me. Sorry about that. All right. and then this guy's green. So your natural line x is here. That 1/4 acts as a shrinking, so it's shrinking the values. Think about here your y values, your output, right? So you're getting 1/4 of the output, right? So that's why it's kind of shrinking the output. As x increases, you're getting 1/4 of the output every time. And then this -2 acts as a, because it's on the outside, it's not in parentheses with the x, it acts as a vertical shift down. Okay, so that's why your whole equation is shifted down. All right, this is where it gets kind of fun, and then you can use Mathway and our shared login to check your work, but you're basically expanding this log. So you're using the multiplication rule and then the exponent rule. So all the exponents jump in front, and anytime you multiply, you just break it up with its base log. So this thing broke up into log 5 x squared plus log 5 a7, which breaks up further. The 2 jumps in front and the 7 jumps in front. The half jumps in front, and that's it. We have 1/3 log base 2a plus log base 2 to the, what is that, b plus 1, yeah. Okay, so here's what I did. So first we're going to combine them because this is different. So we're using the product rule. Because it's plus, you just go ahead and write log base 2 parentheses this unit times that unit. Okay? And then you just kind of distribute it. So you have the a to the half times the b plus the a to the 1/3, times the 1, and then that's it. Okay, so that's the conclusion, and that kind of runs you through your homework. If you have questions, give me a call today, 7 to 8 p.m., and I'll be happy to help you. Good luck!